As we had mentioned on Monday, we said that we were going to be addressing sequences and series first. One thing I will mention right now, just at the beginning, if you have a tablet or something that you can actually write on to take notes, that's electronic, that's fine. I don't want you trying to take notes with your laptops. Okay, so when I'm teaching, you can put your laptops away. They become more of a distraction than they're worth. So go ahead and put your laptops away right now. And as needed, we could get them back out, but it's really not feasible to take notes and keep up when you're trying to type. Okay. Each unit, we're going to have certain essential questions and vocabulary. Those of you who have been here for a while at the school are familiar with these. But the essential question that we're talking about in this unit on sequences and series is, how do patterns of numbers progress? We're looking for patterns. All right. We have a number of vocabulary words here, and when I list things on vocabulary, these are things that aren't necessarily the only vocabulary that you need to know, but they're kind of the most significant ones that you really have to understand well. Okay? So as we go forward, keep that in mind and make sure that as you see those vocabulary words, if you can't, glance at it and know exactly what it's talking about, then you're not quite ready for that part of the unit, okay? These should be kind of no-brainers by the time we're done. They should be really easy for you by the time we're done. Not necessarily today, but as you approach the unit, okay? Let's put cell phones away, please, and focus on what we're doing. Alright, so let's start out by, first of all, laying a groundwork for what we're going to be doing throughout the unit. Some of these terms you may have run into before, some you may not have, but today especially is going to be a lot of foundational kinds of things. A lot of terms, a lot of kind of introductory material. So there won't be a ton of application today, but stay with us and we'll be able to build or have something to build on in the upcoming classes here. So starting off, unit on sequences and series, let's define what a sequence is. A sequence is a function. Now, you guys have learned about functions before, but this is a function specifically where the domain is the set of positive integers. Now, positive integers starting with 1, okay, not 0, starting with 1, 2, 3, and so on, the natural numbers or counting numbers. Okay. Yeah, and they can go on forever, okay? Now, these sequences have terms, all right? The terms, we usually use an A to represent, and then the subscript are these little numbers. Those are called subscripts. So A sub 1, A sub 2, A sub 3, A sub n is how we would read those. But those are the terms of the sequence, okay? Now, every sequence is defined in terms of an A sub n. That's a general definition, and it's going to have some expression involving n in it, okay? So, for example, we could have the sequence that's defined as A sub n equals 2 n squared minus 3. Okay? So if I'm listing the terms for this sequence, I would say that A sub 1 is what I get when I plug in a 1 for n. 2 times 1 squared minus 3. Okay? So that's 2 times 1 minus 3 is negative 1. So that's the first term in this sequence. Okay? You know, a sub 2. I'm just going to use my finger. A sub 2 is 2 times 2 squared minus 3. Alright, so there we have 8 minus 3, which would be 5. Alright, and so on and so on. And the nice thing about this is you can find any term you want by simply plugging in that value of n in. So if we wanted the 10th term, okay, a sub 10 is 2 times 10 squared minus 3. So 200 minus 3 would be 197. Alright, and so you can find individual terms, or we could list all the terms we wanted. So not too difficult, but that's what the definition, if you're asked to find the definition of the sequence, it's asking for some kind of an equation here for a sub n. Alright? Now, one particular type of sequence that's kind of interesting is what's known as a recursive sequence. Okay? A recursive sequence. And the interesting thing is almost every sequence could be defined recursively. Alright? Now, how many of you do any kind of computer programming or something like that? Okay? A couple of you? Have you ever dealt with recursively defined functions? No? Have you? Or okay. It's kind of an advanced topic, but basically what it does is it will define a particular value for like this base amount, but any higher amount that you plug into the function, it'll run the function, and within it, it'll call another version or copy of itself. And it'll keep calling up copies of itself until it gets down to that one that's defined, and then it kind of backfills the entire thing. And I know this may not make any sense if you haven't done any programming, but the idea is each value depends on a previous value. Okay? And that's what a recursively defined sequence is. We have our a sub n that is dependent on the previous value. So for example, I could say a sub n is 3 times a sub n minus 1. That's the previous one. Okay? Now, if that's all I put, we're never going to be able to find any values. Because another part of the definition of a recursive sequence is that you have to define your starting point. Okay? So a sub 1, if we said a sub 1 was 5, then we could find all of the terms. If we wanted the 5th term, that's 3 times the 4th term. Well, what's the 4th term? 3 times the 3rd term. Well, what's the 3rd term? You see how we keep having to go backwards? Until we got down to something that had the 1st term in it, we plug in the 5, and then we can start plugging those values in to get all the ones that we need. Okay? Now, one example of this that's relatively simple is what's known as the Fibonacci sequence. This is kind of a famous one, the Fibonacci sequence. And you'll notice here, both of the first 2 terms are defined as 1. Okay? So if I was listing the terms in this sequence, I would have 1 and 1. Then you'll notice here, a sub n is defined as a sub n minus 1 plus a sub n minus 2. Can someone put that in their own words? What does that mean?
First term plus the second term.
Okay.
Second term plus the third term.
Add the previous 2 terms.
Yeah, adding up the previous 2 terms. So if I'm finding a sub 3, 3 minus 1 is 2, so it's a sub 2 plus 3 minus 2 is 1, so it's a sub 1. Well, that's 1 plus 1. So now I know the 3rd term is 3, or is 2. Okay? And then we can keep finding terms. What would the 4th term be?
3.
3. 1 plus 2?
5.
Good.
8,
13.
13,
And so on. Yeah, it keeps going 21 and on and on and on and on. Okay. But there you have this idea of recursively defined functions. Can anyone anticipate a situation where a function defined like this might pose some real problems? Or might, not necessarily a problem, but might cause us to have to do a whole lot of work?
You're asked for like the 6,000th term.
Yeah. Think about this previous one we looked at. If we want the 6,000th term, we just plug in 6,000, right? What do we have to do if we want the 6,000th Fibonacci number?
Find one.
5,999.
Yeah, you've got to find the first 5,999 of them in order to get the 6,000. Alright? That's why if we can define our sequence in a way that's not recursive, that's preferable. Okay? We would like that better. There actually is a definition for the Fibonacci sequence that is not recursive. Someone figured it out, and it actually, interestingly enough, uses the golden ratio. Have any of you ever heard of that? The golden ratio? Okay. It's 1 plus the square root of 5 divided by 2. Alright, which is this decimal. But there actually is a way where we could find the 6,000th one without having to find the first 5,999. Okay, I don't remember the formula off the top of my head, but it's there. And any time we can define something without using recursion, we would. But this is how recursive sequences work. Every term relies on a previous term, or two. Okay. Now, another aspect that we need to consider here is the factorial. Okay? This is some notation that you need to be familiar with. We have, I'll write it a little bit bigger because it's a little unclear, n with the exclamation point. Okay? That means n factorial. And this is actually an operation, like multiplication, addition, subtraction, those operations. This operation, though, says that we need to multiply all the integers up to whatever that number is. Okay? So if I have a 6 factorial, I'm going to start, and you can either start at the top or at 1, it doesn't matter. But 1 times 2 times 3 times 4 times 5 times 6. Okay? And we multiply all that together, and we should get 720. Alright? Because that's a 10, that's a 12 times 6 is 72 times the 10 is 720. Yes?
Could a factorial be a binomial? Or is it just one?
You can, here's the deal, it needs to represent an integer, okay? Well, I take that back. It's possible to do fractions, but it's way beyond what we're going to do. You may run into a binomial. The key there is to be careful that, for example, if you had 2n plus 1 factorial, should probably move this over. When you are multiplying that, we really don't know what that equals. So it would be 1 times 2 times, and then you put like a dot dot dot. And then what's the factor right before 2n plus 1? Just 2n. So times 2n, and then times 2n plus 1. Okay? Now, we can use expressions like that in a factorial. And usually what we end up doing is we're doing it in some context where we'll end up canceling out, most of this stuff. But yeah, it can be. So, very good question. Yes?
I'm sorry, is the dot 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 everything leading up to what actually n is?
Yes. Yeah, since we don't know what value this is, then we put that just to show whatever it happens to be, it's all in there.
Alright, and you just add the 2n after the last one. After what n is, you multiply that by 2.
Well, no. It actually, the term previous to this one would be, get back to this, 2n minus 1. And the one before that would be 2n minus 2, 2n minus 3, 2n minus 4, until we got down to the 1.
Okay.
Okay? Yes?
I'm sorry, can you explain that again, like the exclamation point with the N? Like, I don't get what you just did, like up there.
Since we don't know what this value is,
Okay.
we know we have to multiply everything up to it. So we start at 1, 2, and so on. And then these are integers. So let's say this was 11. 11 minus 1 would just be 10. 10 minus 1 would be the 9. You have to just subtract an integer each time to get to the previous factors. Yeah. We'll deal with those a little bit, but for the most part, we'll deal with ones that have numbers involved. Now, one thing that is helpful is to be able to reduce fractions that have factorials in them. Okay, because as we're going to see in just a moment, we're going to use these two formulas for permutations and combinations and permutations. Okay, you'll notice they're both fractions. So before we get to those formulas, actually, let's look at my scroll bar isn't showing up. Oh, maybe that's all I get. If let's say I had 16 factorial, that's going to be a real big number. Okay, and I don't know about you, but I don't feel like multiplying all of that out. However, if I had a problem where I had a 16 factorial that was over, let's say, a 13 factorial, I actually don't have to multiply out either of those. I can cross out the factors that are in common, right? Because these are multiplication. So yeah, if we expand this factorial out, it's 16 times 15 times 14 times 13, 12, 11, 10, and so on. What is all of the rest of it?
13 factorial.
It's 13 factorial. Okay? So now, when I'm dividing by 13 factorial, all of that cancels out to 1 because it's multiplication, right? You can cancel things out when it's multiplication. So now I just have to do 16 times 15 times 14. Okay? So I get 210, 420, 840, 1680. So come out to 1680. Is anyone checking me? Or check up on me. You never know. Might mess something up.
I got 3,316. Did I make those one?
I didn't go far enough.
33, it's 3,306.
Yeah.
Okay, I needed to double it again. Oh, come on. See, I told you you have to check up on me. Sometimes I didn't go far enough. I only doubled it 3 times instead of 4. Alright, so we get 3,360 for that one, which is still somewhat of a big number, but it's a whole lot better than actually figuring out what 16 factorial is. And in fact, some of your calculators, depending on what kind of calculator you're using, it won't even do. I mean, it may give it you in scientific notation or something, but it's a lot easier if you reduce first. Okay? You got it? Okay, cool. So let's talk about the application that we'll run into this with the most, and that is the combinations and permutations. Okay, combinations and permutations. With both of these operations, you could call them, we're dealing with picking out a certain number of items out of a total number of items. All right? So in both cases, we have n, we usually use n and r. We have n things to choose from, and we're going to pick r out of them. Okay. Now, the key difference between these two is whether we care about the order we're selecting them in. Okay? No, I left that in my... Thought I had something, but I forgot it. What do you lock your locker with?
Master lock.
Okay, do you know what those are called? Like the padlocks, another name for a padlock. It actually does need a permutation. They're named wrong. A lot of people calls them a combination lock. All right. The fact of the matter is, though, does it matter what order you put the numbers in? Yeah. Okay. So really, we ought to call those things permutation locks. All right, because the order matters in a permutation. In a combination, the order does not matter. You might say, well, how will I know when the order matters? You have to consider the situation that you're dealing with. All right, for example, we have 19 people in here, and let's say that I was going to pick 11 of you to play soccer, okay? If I pick 11 of you, does it matter who I pick first? No, because I'm just picking out a team, right? Everyone has an equal position. I'm just creating a group. Right. So in that case, if I wanted to pick 11 of you, if I wanted to pick 11 of you, I have 19 to choose from, and I could do 19 choose 11. There's the notation that we can use. 19 choose 11. Another form of notation for combinations is right here with the parentheses. We would put 19 above the 11 in parentheses. This is not a fraction. Do not write it with a fraction bar in it. Okay? It's just 19 over the 11, and that says the same thing as this does. Okay? So that's how we could pick 11 people for a team out of the 19 of you. All right? Now, let's say that instead of just picking a team, I was going to pick you, and the first person I picked was going to be the goalie, and the second person I picked was going to be the left striker, and the third person I picked was going to be the right striker, okay, and so on. Does the order I pick people in matter then?
Yes.
Yes, okay. Or if we're running a race, and what's our finishing, the 11 people who finished first and the order that they're in, okay? The order there would matter. That would be a permutation, so we could make it 19 permutation 11, okay? Now, question, well, let's set them up first, and then I'll ask that question. So notice here, the n is the number that you're choosing out of, and that's always going to go in the numerator in both cases. So we've got 19 factorial. All right. Then, in the denominator, we have n minus r factorial. What's n minus r? 19 minus 11, so that's our 8. Okay, so we have 8 factorial. Now, here's the cool thing about this. If you understand this, it'll really help you understand the whole formula. The 19 factorial would be if I were taking all 19 of you and putting you in order.
So it would be 11 factorial.
Not quite.
Well, could you...
It would be 19 times 18 times 17 down until 9.
Yes.
So,
Yeah.
Yeah, it's the same thing, it's just actually 19.
Alright.
Okay. So the 19 factorial is if we put all 19 of you in order. But if I only want to put 11 of you in order, how many do I not care about? 8. This eliminates those other 8 that we don't care what order they're in. Okay? Now, over here with the combination, I still have 19 factorial. The n minus r eliminates, that's the 8 factorial. That eliminates the 8 people that we're not concerned about right now. But I also need to eliminate all the sets where I have the same 11 people, but they're just in different orders. Okay? So the way I do that is with this r factorial. 11 factorial. What that does is I've got this 11 people, but I picked them in a different order. There's actually 11 factorial different ways that I could arrange U11 in a straight line, okay, or in order. But I don't care what order you're in, I just want this group, okay? So this 11 factorial that we divide by eliminates all of that repetition, okay? Now, which of these numbers is going to end up bigger?
Combination.
No, permutation, because combination has a lot more in the denominator.
The permutation, because there's more options.
No, the combination, because it could be any related permutation, just the one.
No,
It
it's
should
be the
permutation.
combination.
If you look at the combination,
Can
there's
you
more.
repeat with combinations?
There would be a larger
You
number.
can't repeat factorial.
Can you repeat
No,
what?
you can't repeat.
Like, because you said in permutations it says you without repetition, but in combinations it never says without repetition. So can you?
Oh, no, you can't, sorry, you cannot repeat. I get what you're saying. I thought I had fixed that. I must not. Oh, my computer crashed. That's why I didn't save it. Sorry. This is without repetition as well.
Oh.
Okay, I get what you're saying. Like if we could pick the same person twice or something. Yeah, that is a whole nother, you have to do a lot of other stuff to be able to do that, but.
The combination formula will inherently have more in the denominator.
So it'll be small.
So that would be smaller, so permutations would be the larger number.
Okay, that's true. Alright. Notice here, we're only dividing by an 8 factorial. Here we're dividing by an 8 factorial and we're dividing by 11 factorial. So we're dividing by a whole lot more. So the combination is always going to end up being a smaller number. Okay? Now, when you're evaluating these, I recommend simplifying first. Okay, someone already mentioned this 8 factorial is going to cancel out the 8, 7, 6, 5, and so on. So this is going to be 19 times 18 all the way down to 9. Okay, and just for time's sake, we won't do that because you know how to multiply. Alright, but we would just multiply all those values together until we got down to 9, and that would be how many permutations of 11 people we could have out of 19. Here, however, I will actually go ahead and simplify this one. And I'm going to copy it and move it to another slide so I can have some space to work. Okay. When I do this, we'll simplify it, and it's actually a little easier than you might think. Okay. We know that the 11 factorial is going to cancel out with the 11 and on down from the 19. Okay.
12,
17, 16, 15, 14, 13, 12, and then 11 factorial. Okay? So like I just said, the 11 factorial will cancel with the 11 factorial. But we also have this 8 factorial. So 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Right, now, the nice thing about that, wrong one, go, a different color. Nice thing about that is we actually still can reduce a little bit more, okay?
16 and
16 and 8, 14 and 17.
Right.
14, 7,
Yeah.
12, and 6.
12.
Here's a 16. Let's take it one at a time here. Here's a 16. 16 is 8 times 2, right?
Mhm.
So I could cancel out both of these with the 16. Okay?
15 is
doing?
5
6
times
and
Hang on.
3.
Yeah.
6 and 3.
So yeah, 6 and 3 make an 18. I think I'm on. Yeah, stop doing that. That's. There we go. It just went to pen. Red. There we go. So yeah, the 6 and 3 make 18. We can also cancel out some parts, like 7 goes into 14 twice, so we'll leave the 2 there.
5 goes into 15.
Yeah, 5 goes into 15 3 times.
4 and 12 3 times.
Yeah, 4 and 12, we got a 3. So it may look a little bit messy, but if you're careful, you actually can reduce this entire problem down to 19 times 17 times 3 times 2 times 13 times 3. Which is still a bit, but it's not as bad as it originally was.
75,582.
Okay? So, with the 19 of you, I can make 75,582 different 11-person teams. Okay? Just kind of amazing to think about. But if you break it down, it actually makes sense. You know, here's 4, 8, 9, 10. With these 10, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 different possible teams, picking one of the other 9. Alright? And then you guys can see how we get a lot of options really fast. Okay. But that's how we can simplify with permutations and combinations, simplify the factorials. Alright, and we will use those a bit here as we look at our sequences and series. Okay? Alright, so we know what a sequence is. We talked about recursion. We've talked about factorials and permutations and combinations. The next thing I want to look at is sigma notation. Alright? Or summation notation. Right? Again, we're hitting a lot of different kind of things today that build a foundation for the rest of our unit. Sigma or summation notation. The reason why we have 2 names, alright, a summation or sum, adding things together, that's what we're doing here. We're adding a bunch of stuff together. That's called sigma notation because this symbol right here is the Greek capital letter sigma. It's the Greek letter S, but it's called a sigma. Now, we use this notation quite a bit because this is actually kind of the bridge between just dealing with sequences, which are a list of numbers, to dealing with series. A series, as we'll see in a moment, is the sum of a list of numbers. Okay? So here's where the sum comes into play. You can see here we have the a sub 1, a sub 2, all the way up to a sub n, just like we did with our sequences, but now instead of just listing them, we're adding them up. Alright? So let's look at this notation and what it tells us. The sigma says the sum, and then here's the notation, that's an I. It says the sum from I equals 1 to n of a sub I. Now, it doesn't necessarily have to say a sub I, it could be any expression, but it's going to have an I in there somewhere. And what will happen is, each term, you start with I at whatever number is down here, in this case 1, and you figure out what this equals when I is 1. Then you figure out what it equals when I is 2. And then you figure out what it equals when I is 3. And so on until you get to whatever this n value is. Okay? Now, that I is what's known as the index. Okay, it's called the index. The one, that bottom number that we're starting with, is called the lower limit of summation. Where you stop, the n, is the upper limit. Okay, so you're going from the lower limit to the upper limit. Just to illustrate this, we could have the sum from I equals, let's say it's I equals 3 to 7. It doesn't have to start at 1. Okay? The sum from I equals 3 to 7 of, let's go with just a simple 2i. Alright? We want the sum from I equals 3 to 7 of 2i. So what we do is we'll start out doing 2 times 3. That's going to be the first thing that we're adding up. Then we're going to add to that 2 times 4. Okay? Notice that this was our index, I. It's going to increase. Now it's 2 times 5. Then 2 times 6. Oops, we're adding.
All up to 7.
Plus all the way up to 7. Now we stop. Okay? We can add that up now by simplifying. We've got 6 plus 8 plus 10 plus 12 plus 14. Okay, is it 30? 24.
50, sorry. Yeah, that's what I say, 50.
Yeah, 24 plus 12, 36, and 14, yeah, 50. There we go. Alright, so that's what that sum would equal. Now, there are some properties that'll make it a little simpler. One, you actually could probably see here. What do you notice all of these terms have
2 times.
2 times? What do you think we could do?
Square. Square.
We can't square it.
I would take
Factor
the
out.
two and put others in parentheses.
That's right, we can factor it out. We can take the 2 out and put the other numbers in the parentheses. Okay? For example, what would we call that 2 in this case? What's the name for that when we have this 2 being multiplied by all of them?
Factor.
It's a factor, it's a common factor. Greatest common. But yeah, it's a common factor. So we actually could rewrite this as 2 times, and then what's left? A 3 plus a 4 plus a 5 plus 6 plus 7. Alright, if you add these up, we have 25. 25 times 2 is 50. Okay? And that actually leads us to one of the properties that we want to look at. That's right here. If we have a constant times whatever it is that has the index, we can pull that constant out. Alright, so here we had c times a sub I. So we pulled the c, the constant, outside of the sum. Okay? Now, there's a lot of notation up here. I would recommend you not try to just memorize all the notation, because you're going to get lost. Memorize the concept. Alright? When we have a constant times something, you can pull the constant out. You're factoring out a common factor. That's really what you're doing. Let's look back at this first one. Notice we have just a constant. The thing inside of our sum doesn't have the I involved. This would be doing something like this. I equals 1 to 5 of 4. Okay? So let me ask you, when I equals 1, what does this expression equal? When I equals 1, 4 equals 4. Alright? When I equals 2, 4 equals?
No, 4 still.
4 still equals 4, right? When I equals 3, 4 equals
Four.
4. And when I equals 4, 4 equals 4.
What's the point of that?
And when I equals 5, 4 equals 4. Alright? The point is that the I actually doesn't impact the value that we're adding. So, notice the property up here. It says, how many terms are you doing this for? That's how many of that constant you're going to have. That's really what the definition of multiplication is. You're adding the same thing a bunch of times. So we can just write this as C times N. So instead of writing all this out, I could just say it's 4 times. There are 5 terms here. 4 times 5. So we've got, oops, wow, that's ugly. 20. There we go. Alright, that makes sense? It's kind of one of those ones that's so easy it's hard to understand. Because it just makes sense.
So what does I do?
The I really just tells us how many of these we've got. Okay, it's still changing, we just don't happen to see it in this case. Alright? Now, the last two here, basically all they're telling us is that if the thing that we're adding up has multiple terms in it, we could split it up into separate sums. And we're allowed to do that whether it's addition or subtraction. Okay? So, that's why I have this sum right here written for us. Let me erase so we have some room. Okay? Because I can use all three of these rules to actually simplify this a little easier than we could just by plugging in 1, 2, 3, 4, and 5. I could rewrite this. No. I want that. There we go. I could rewrite this as two things in separate sums. Okay? So I could have the sum from I equals 1 to 5, and then plus another sum from I equals 1 to 5. Alright? Here, I would just be doing 4. Okay? What would I be adding up over here?
Nine.
The 3i. What can I do with that too?
3 up.
Pull the 3 out. So I could have 3 times the sum from I equals 1 to 5 of just I. Alright?
Wait, why can you pull the
This property right here that we had seen, because that 3 is a common, well in this case it was a 2, but it's a common factor.
Oh, okay.
How do you solve it from there?
So now,
Let's get
what does this equal?
20.
20, because it's a constant, right? So that's nice and easy. And this, really we're just adding up 1, 2, 3, 4, and 5, right? And what? And then we'll multiply by 3. So 1 plus 2 plus 3 plus 4 plus 5 is 15. So 3 times 15 is 45 plus 20 is 65. Alright? Does that make sense?
Did you just do three? Wait, where'd you 15 from?
1 plus 2 plus 3 plus 4.
Oh, okay.
Yeah. Now, on this one, did we really save ourselves much time? Probably not. But if we were doing the sum from 1 to 100 or something, we could save ourselves a lot of time. And if not time, it at least would keep our numbers smaller. Okay? Because you'd have 4 times 100, that you could just have that 400 sitting here and deal with the other part separately.
But wouldn't you still have to add 1 from 100?
You would. But there's a formula for that actually.
What? You do 1 plus 100. 1 plus 100.
Yeah, it's like
And divided
Is it an
times
ace
50.
of formula?
Yeah,
Yeah.
1 plus 100 times 50.
1 plus 100 times 50, yeah, so it's 5,050. Actually, interesting story about that, I'll tell you this. Have you heard of Carl Friedrich Gauss? He was a mathematician. Okay, he was really cool. He was like I think he was like 8 or 9 years old when he figured this out. His teacher, he got in trouble because he was kind of a smart aleck too when he did this, but his math teacher wanted them to practice their addition, so he had them add up all the numbers from 1 to 100. And back then they used these little chalkboard slates that they would write on in class because they didn't have paper. It was back, I think, like the 1600s or something. They didn't have easily accessible paper. It was expensive. So they'd use slate. So the teacher told him to do this, and like 2 minutes later he walks up and just tosses the slate on his teacher's desk, which is a little disrespectful, and had the answer just written down. And he explained it to the teacher how he got it, and it was right. And that's what he did. He saw that 100 plus 1 was 101, and 99 plus 2 was 101, and 98 plus 3 was 101, and he would end up with 50 of those. So 101 times 50 was 5,050. So he was able to figure it out. He was a pretty amazing mathematician. He was able to figure out the answer, 5,050, without having to do all the addition.
They laugh at you.
So. Well, he wasn't laughing after he got punished for being disrespectful, so, but he made up for it later. He was pretty brilliant. Came up with a lot of stuff.
How do you do that at that age?
So, what?
I don't know how you would do that at that age. I would never think of that.
Well, he was quite gifted. He made a lot of discoveries in mathematics in a number of different fields. I mean, he was just brilliant. So, all right. Let's see. The last thing I want to look at, and then we're going to do a little activity to see how much of this is kind of sunk in, is actually getting to the series. Okay. I mentioned that the summation was the bridge between a sequence to a series. And what we actually are doing when we find the sum is we're finding the sum of a series. Okay? Now, as you've noticed when we've looked at sequences, what happens to the numbers in the sequence?
Get larger.
They just keep getting larger and larger and larger. So if I ask you to find what's the sum of all the terms in this sequence, what's going to happen?
Oh.
It's infinity, okay, for a lot of them. There are cases, though, where we're actually able to find the sum of the entire series, okay, the infinite series. There are cases in the geometric, and there are other ones. We'll actually look at one where we can find the sum of the series. It's kind of cool. But most of the time we have to limit ourselves to a certain number of terms. Alright, and that's what's called a partial sum. Okay, a partial sum. Now, a partial sum, if we're talking about the third partial sum, that means we're going to add up the first 3 terms of the sequence. If we have the 10th partial sum, we're going to add up the first 10 terms of the sequence. Alright? So we're not trying to be tricky or anything here. It's just whatever partial sum, that's how many terms you're going to add up. You can write this a couple of different ways. There's actually one more way I'll add to this. You can actually list out all the terms, a sub 1, a sub 2, a sub 3, up to whatever n is. Okay? You can write it with the summation notation, I equals 1 to n. Or another way is just to use a capital S sub n. Okay? So if we were doing the third partial sum, we would call that S sub 3. The 10th partial sum would be S sub 10. Okay? So if you're asked to find S sub 5, they're looking for the 5th partial sum.
So if you were doing the sigma notation and doing the 10th partial sum, the number on top would be 10.
Yes, exactly. The 10th partial sum or the third partial sum here, sigma I equals 1 to 3 of a sub I. Over here it would be I equals 1 to 10. I like the S notation, it's just a little simpler. But you'll see both. Now, if we want to indicate that we're finding the sum of an infinite sequence, instead of putting an n, and instead of stopping at n, we'll put this ... the ellipsis we call it, at the end. And that just means we keep going forever. Or if we're using the summation notation, we'll put the symbol for infinity as our upper limit. Okay? If we're using the S notation, we'll just use an S and put the symbol for infinity next to it as the subscript. Alright, so not too bad. Not too bad. We're just adding stuff up. So let's try one here. We want to find the third partial sum for this series. Now they defined it as an infinite series, but we want to find the third partial sum. So if you'll notice here, I did the sum from I equals 1 to 3. Alright, take a moment and try to figure that out. It's 3 over 10 to the I power. That's what that says. 3 over 10 to the I. You have it?
Right.
Hang on a second.
That I just did.
Oh, okay. Okay, so we're going to be adding up 3 terms. What do you get when you plug in the I equals 1? 3 tenths?
300.
3 100ths? And 3 1,000ths. What does that come out to?
0.333.
Ah, and you kind of saw the key to our next step. This is 0.3, right? And this is 0.03. And this is 0.003. Okay, so that is 0.333.
So that's 1/3.
Okay,
No wonder.
well, the third partial sum is only 0.333, or 333 1,000ths. However, the second part of this problem, which doesn't want to show evidently, whoops. That's why I locked it. Here we go. If we kept going and found the sum of the infinite sequence, what would we end up with? Each term,
That's 3. That's 0.333.
0.333. Every time we go up another power, it's going to give us another decimal point. So, we could say that the sum here equals
0.3 repeating.
0.3 repeating, which is 1/3. And this is what I was telling you. There are cases where we can find the sum of an infinite series. This is one of those. Okay?
Will it only be one that's a repeating decimal?
Not necessarily, but we'll see as we get. I think Friday we'll see. So. Okay. Any questions?
I just need to go to the bathroom.
Okay.
Sorry.
All right. Any questions about what we're doing here? Okay,
Wait,
yes.
it sounds stupid, but, I don't know why it's not 3/20, 3/30 instead of 3/100.
Oh, and it may just be because it's written small here. This is 10 to the I power.
Oh, I was
It's
looking
10 to the I power, not 10 times I.
at that. Okay, yeah.
Okay. No, that was a good question. I don't want you to be confused. It's small. Some of these, I'll take a screenshot out of the book, and sometimes they're a little bit hard to read, so I'll try to make sure I clarify it for you. Okay, so what I want to do at this point is kind of see how much has sunken in. Alright, and we're going to do this somewhat regularly. So if you'll go, you can get out your laptop or something like that and go to Socrative. Okay. You'll go to Socrative. Remember, if you go to my class website, over on the right-hand side,
It's Socratic.com.
yeah, you can go to Socrative.com. Just make sure if you go that route that you click on the student login. Okay? And remember that the room name is Hickson NBPS. And we'll do a space race. Let's see, we've got 19, well right now we have 18 people, so I'll divide you into 6 teams. 6 teams. There it
What's
is.
the name?
Hickson NBPS. We'll auto assign teams. What do you guys want to race? You want to race rockets?
Yeah, let's raise rockets.
Or a bear, or a bicycle, or unicorns? Alright, we'll do unicorns. Okay.
We're so happy.
Let's just.
Yeah, it's
Alright, so has everyone gotten there and it says waiting for teacher?
Yeah.
It looks like.
Mom,
Alright, so you're all waiting.
Some people that aren't.
But what is it?
Okay, it's alright, it's not necessarily time, but alright, that should start for you now. We'll see how you guys do.
What's the room color here?
Here's
Matter where we make her.
Nah, won't let me join.
Hickson,
Oh wait,
H-I-X,
I don't know what team I'm on. Oh, that's
S-O-N.
in teal.
NBPS.
Wait, did we go?
Oh,
Yes. And then make sure you put your name in, last name first, and then your first name, just like it shows you there.
Put my first.
Is this really stressful?
Were you able to log in? Yeah, hit refresh, see.
Who else is on my team?
Yeah.
Oh, there we go.
It's on my team.
Is it? And if you need to look something up in your notes, you can. We're gonna do this a lot, so don't.
It's a game.
First end terms.
You remember exercise rather than the sequence?
Is yours not working?
Mine just won't load, so I'm working with him.
Okay.
I tried reloading it like 6 times. It always.
Oh, there we go. All right, we're all neck and neck here.
Come on, mine.
Let's go.
It's an MVP.
Picks and MVPs. Okay. Just trying to get them into it again, I'm sorry. If you're watching the video, I'm sorry we can't pause it. So, but we'll go over the answers in a minute.
Is it whoever finishes first or whoever gets most right?
I think it's whoever gets most right. But like in the event of a tie, we'll go based on who gets to the end
Are
first.
there any capitals in Hicks and MVPS in the code?
No, it's not case sensitive. Oh, you forgot the S.
Oh, yes, no, those make
How do you do fractions? Like,
Some
how-
sticks.
What?
With the slash.
Okay, so like that would be that.
Yeah, that's how you could write a fraction. Don't forget to reduce fractions. Okay. Yes.
So this one I'm pretty sure I put the correct answer, but it just
Is that listening in terms of the sequence? Yeah.
is it just like
Yeah.
not
Let me
right?
see what you did.
Yeah, put it like it says it's wrong.
Oh, mine says
Yeah, it did say that for two
Mine's only-
Oh, you know
questions.
what?
It said that for me too.
Did you
Some of you
I
guys-
got it wrong.
Well, here's the deal. I put in possible correct answers,
Oh,
and for
that's-
one of them, I put spaces after all the commas,
I did
and for one of them, I put no spaces after any of them. But I think it marked yours wrong because it has.
I put spaces.
For which one?
No, what it is some of the,
It might-
some of the information is wrong. Yeah,
The first one?
the answer's loaded.
One of them says find the sum, it's not in there.
Oh, no, there's a
it takes a
picture.
second. It takes a
Wait
second.
for the picture to load.
That's a fraction.
So it's not a perfect system because you're typing in numbers
I
and
just wanna
stuff.
know if
So
I like
I
actually
tried
got
to anticipate different ways you guys would write in the correct answer, but in a different form. Now, the one thing that it won't mark correct is if you don't reduce your fractions, it's going to mark it
Yeah,
wrong.
I just told me I was incorrect and I put spaces and it had no spaces.
Well, which one? Oh, what did you put? Did you put in -1/1?
Yeah.
That's right.
That's nice.
But that's where
That's like.
simple. Make sure you simplify. Okay. Oh, blue looks like reached the end.
Yes.
Wait.
Who's
The
on
last
blue picking up the
The last couple are tougher.
Blue picking up the
Now, listen, don't worry because none of these things that we do in class will be graded, okay? You may see like a formative assessment mark in the grade book, but it's not counting towards your grade.
coming down to the wire.
No, then that's fine. I just listed it.
Wait, which one was negative one, positive one, negative one, positive
Were you
Yes.
here for
No.
success again?
No, I
Did
didn't.
you put like
Okay.
maybe one over one?
I was here for
One.
Okay, that's why.
I was here the whole
For
time.
number
City.
nine,
Because
it
it's
is-
so
Yes, that's
simplified,
right.
it's just an over one.
just letting out of
Yes. What, there's nothing.
Not
And then the other one.
Oh, I get it.
Here comes
I
the
get it.
judge.
Now I'm
was supposed to
thinking
be
it's fine.
71.
Why doesn't it say completed?
I don't know if
No.
that's right.
No, I got it.
Well, 'cause like it's
Magenta
the teams.
I did it like that.
reached the end.
You don't need to do that. You can do
I already finished, but
2 times 1.
Oh, it just says, yeah, it says you're finished and you're waiting, cause
I'll hit finish, and I think it might give you a summary or something of your answers and the correct answers and whatnot at the end. I'm still learning how
This is
to.
a cool program.
Purple's
It really
for,
is. I
people
just
hot tanks
Found out
smashing
about
up.
it recently.
They pushed it onto our iPads
No,
last year.
I
but
finished.
nobody used it.
it just won't go.
Some people use Kahoot, which is
No,
similar.
that's not how it
yeah.
does the-
We
It's a
use that
similar
for
thing.
a
I
couple
just
classes.
I got into this and I really liked it.
Question
So-
answered correctly.
Yeah, Kahoot was good too. I liked Kahoot.
No, I didn't. Someone's character.
The only reason I picked this one really over the other was because it has like a template. Oh, cool. Yeah. It has an Excel spreadsheet that I can type all the answers and things into and then just upload it rather than having to do it with the GUI
Who else was on
interface.
Magenta? Who's on Magenta?
Team Blue.
I'm really old.
Look, Magenta's caught up.
Alright.
Me.
Yes. Is it about correct answers too, or just who's done?
I'd say correct
I'm not sure.
answers.
I think it's
Oh, it might give like a correct answers thing at the end, like who.
Yeah, I mean, we'll look at who got, like, how many you guys got right and whatnot. I think this is just how many you've responded to
Who's green?
so far.
Shut up.
Probably just too
It's
lazy
not
to
just
do the
one
last
person. That's the nice thing about this. It's a low risk. It's like kind of a competition, but you don't know who all is on your team, and
I was too lazy to think through the last one. I was just like, okay, I'm gonna
Which
put
one?
this in.
Dark blue or? There is only one. There's like a.
There's no
sort of
it's a
violet
skill
teal.
Right, rewind or?
I was on
I was on the bathroom saying suits.
Oh.
No, that let's
Okay,
just respond.
perfect.
I got more questions. Correct.
I got 2 wrong.
Did you miss any of the other ones that weren't sequences?
The one that was 2i plus 1.
That was a sequence.
So basically 2i plus 1.
Oh, it's not.
What did you get?
I don't remember. Cause that's wrong. 2i. It was like 1 of 5. It was 3 plus 5 plus 7 plus
Is there anybody else?
Yeah,
27.
Can it be written as a decimal or a fraction, please? It can be decimal or a fraction?
except for the one that I said use a fraction, I think you're past that one. Are you on the last one?
Yeah.
Yeah, that could be
There we
the.
go.
The first one was.
10, 15. Then I got
No,
5.
it's one.
So 20.
What's your round two?
First one was cases, right?
Yeah.
Oh, I know they did wrong.
Oh, so I didn't fractions right.
I didn't know.
Actually, you should have had the.
I said 1.79
That's
instead
right.
of 1.8.
Oh, you know what?
And then.
This should
What
be
is
one.
this?
But 9, oh.
Because it's got the plus one.
Yeah.
Why did I do that?
I did
We're
3
losing now.
to, the square root is like 10. I said 9 and I said 10 plus
The only
1.
one on my team.
Okay.
What?
I don't know what I was.
That's
Really?
6.
How? Oh, because it's 19.
What team were you on?
Everyone has 3 and then you have 1.
Are you blue?
No, because there's 6 teams. There may lose 17.
So one team has 4.
4. Then you're not by yourself. You're with at least 2 other people. No, there's probably with 3 other people. There's probably just people not listening to you.
What team?
All
Are
right.
you done?
Who else still working?
Someone's still going? Come on.
Okay, a couple are still working, that's alright. We'll go over the answers here, ones that you guys might have struggled with. The nice thing is it tells us like how much of the class or what percent of the class got it correct or incorrect. So we can identify ones that were commonly missed quickly.
What if nobody got one right?
Then we would take some time to look at it and see why.
If nobody got one.
That's what's nice about this. And really, guys, what this right here is doing is eliminating about a third to a half of the homework I assigned last year when I didn't have this, because these ones that are a little easier, but they're just more straight using a formula, we can identify if you know how to use the formula or just know the facts here in class and address those issues. The independent practice that I assign, which we'll talk about in a minute, is more problem solving oriented and more higher thinking than these ones are. Okay? These were pretty straightforward, just plug in numbers or what's the term, those kinds of questions. So,
Is there anyone still going?
you all set? Okay. Oh wait, hang on.
There's only 13. You might have been the only one on yours.
That's where my grade team's at.
Wait, no, everyone plugged in? Yeah, you
I'm not sure what this is all about, cause like it
Oh,
just,
people are probably
it's
logging.
it's never exactly what.
Wait, Ben, click back onto the software. It was on my iPad. So it just went back up.
I can see it.
Click off. And it went close down. So you have to be like actually on that screen.
I didn't see it moving.
Oh, look, people want to.
Alright, we'll give you another 30 seconds or so here, and then we'll cut it off. And look at the results.
Finish. I think
It is really cool this way.
is everyone.
Is it?
Only or is that?
This is the thing, turn up the down here.
And we have the colds.
I remember last year, this is when my scope was really turned up.
So I grew up in Ohio, so I don't get cold down here.
I was born here and I'm still not cold anywhere.
I think 50 is cool.
Yeah, 50.
I used to play soccer, and soccer season went from beginning of August through October, and usually tournaments at the end of October we'd at least have one game in the snow. So I played a tournament one year, 2 games in one day, and it went from like 35 to 45 degrees, so we had rain and sleet and snow throughout the whole day. It was a miserable
I
day.
can't decide to know if that's worse than the one time I played a baseball game in 110 degree weather.
Oh, that would be nasty.
Yeah.
Alrighty, we're gonna cut it off here and look at our results. Alright, let's look at the chart of results. Here, we'll do that. Okay. Alright, so let's look at percentage-wise.
Nobody got everywhere.
Oh no, that one, someone must have logged in and logged off. I think that was when you logged in and logged off. That's no biggie. Alright, so 95% got number 1 right, 84%. So these look pretty good. Alright, so we've got a couple at the end here that we need to look at. Some of these, though, let's see. Alright, if you put -1 over 1, okay, and I understand maybe it was a little misleading. I said write your answers as fractions. Okay, if you did that, I'm sorry. My intention was if it doesn't come out evenly, write it as a fraction. But if you have things like this that are over 1, you should write it just as an integer. Okay. So we had a couple of those. But let's look at problem number 8. Okay. Write the first 5 terms of the sequence as fractions. Okay. Whoop. All right. It's not showing me. Why is it? Oh yeah, I'd have to move the page over. Okay. So, here we have, this one was marked wrong, but it's just because of the 1 over 1. This one the same thing, okay? So here when you plug in 1, you have -1 to the first power over 1 squared. That's just -1. The alternating sign is something that you'll actually see happen quite a bit. And that's because we have this negative that's being raised to a power. Okay? And notice it's going to go odd power, which will end up negative, then an even power, which will end up positive, then an odd power ends up negative, even power ends up positive. So you're going to see this alternating between negative and positive a lot when you have a negative like this that's being raised to a power. Okay? Let's see. So there you had to simplify. I think that one was, I think we're kind of okay on that one now. Back. Let's go back to, whoa. Okay, here we go. The other one, let's take a closer look at number 7. Okay, writing down the first 5 terms of the sequence. Okay.
What's the answer?
The answer, if you plug in 1, you'll get 2 minus 1 is 1, and you'll get 2 plus 1 is 3, so your first number should be 1 times 3 is 3. Then when you plug in 2, you get 4 minus 1 is 3, 4 plus 1 is 5, 3 times 5 is 15. So 3, then 15,
There's a pattern.
okay? Then 35, 63, 99, okay?
Just like multiply the odd numbers.
Yeah, yeah,
The last number was the first one.
good. Yeah, that's right, okay? So yeah, so the correct answer here should have been 3, 15, 35, because you had 1 times 3, 5, or 3 times 5, 5 times 7, 7 times 9, 9 times 11 is what it ended up being. So this is our correct answer right here. Okay, so we had quite a few there. Were we trying to do that one in our heads?
Probably. I agree.
Okay, that is one thing. Don't be afraid to write out your work. Okay. My guess is with the last one, that was probably the issue as well. Okay. Okay. All right. So yeah, here. This one, okay, this person actually found all the terms correctly, but it said find the sum. Okay, so you just need to add those up. And we did get, you might have gotten 18 tenths, but do make sure you reduce down to 1 4/5 or 9/5. Okay, or I would have also taken 1.8. Any of those answers would have been fine. Okay. So, now, for tomorrow, I have listed here some independent practice problems. Notice on 71 to 77, you only have to do the odds, okay? Now, let me show you something and mention a couple things here. I have already exported the notes for today. Okay, remember on the class website, over on the right here, you can get to class notes. It's there as a PDF. If you look at the last couple pages of the PDF, you will see the independent practice as well as screenshots of the problems that were assigned. So if you don't want to bother going into the actual textbook and finding them all, they're right here. Okay? So there's your
Thank you, Mr.
problems that you need to do. That'll kind of streamline the process, and I need to change that. That's independent practice now. Okay? So, oh, I should have saved. The other thing is this, okay? If the possibility of taking a retake or retest or requiz is even a possibility for you, understand, have you guys seen the student request for reassessment form? This is new this year. Okay. You will have to fill this out. And then I will give you certain tasks that you must complete before you can qualify to reassess. The very first one here, complete all formative work associated. You've got to show it to me. So what you do tonight for the independent practice, keep it. All right? Label it with, the page number or section number. This was section 8.1. Keep it. Hold on to it, because if we get to the end and you decide, I want to take a retest, but you don't have your homework, okay, you've got to prove to me that you did it all. So either you've got to find it, or you're going to have to redo it all, okay? Otherwise, you will not be able to take a retest. That's guaranteed. Everyone that asks for a retest will have to show me that, plus some other things, okay? So, all right. Have a great day. 11th and 12th, yeah, you have advisory.
And 9th graders go to lunch now, right?
Yes.
Thank you, Mr.